So good day, my name is Mark Gabriel B. Cuenta, and today I'm going to discuss the experiment which is focused on the pulse width modulation and demodulation. So the topics are the pulse width uh, modulation and the pulse width demodulator. So moving on to the pulse width modulation. So the pulse width modulation is a technique where the width of the pulse varies according to the amplitude of the input signal. So instead of changing the signal's amplitude, the PWM encodes information through duty cycle variation, making it efficient for digital systems. Next is the procedure. So I use the previous circuit given to us in the previous activity, which is the PWM circuit, wherein this circuit is a pulse width modulation circuit generator built around a 555 timer IC operating in a comparator-based modulation mode. So the 1 kHz sine wave input in the Vin is AC coupled through C3 and combined with the internal threshold threshold triggering levels the 555, while the resistors of R1, R2, and R3 are set and biasing and controlling the sensitivity. So the diode D1 or D1N4148 provides directional changing and discharging paths that influence how the timing capacitor C1 responds, helping shape the pulse behavior. So overall, the circuit compares the instantaneous value of the sine wave with the internal ramp threshold levels of T555, producing a PWM signal whose duty cycle varies according to the input signal amplitude. So moving on to the output, wherein the output waveform shows a high-frequency PWM signal, which is the green one on the bottom part, whose pulse width changes over time, following the low-frequency sine wave, which is the blue one or the input signal. So when the sine wave is at its peak, the pulse becomes wider, and when the sine wave is at its minimum, the pulse narrows. So this demonstrates the successful modulation where the analog sine wave signal or information is encoded into the width of the digital pulses and results a dense switching signal that passes through a low-pass filter and can reconstruct the original sine wave, confirming the proper PWM operation. So that's it for the PWM modulation. Now let's move on to the PWM demodulator. So the pulse width demodulator is the process of recovering the original analog signal from a PWM signal. So this is achieved by processing the pulse signal to extract its average value. So in this process, a low-pass filter is used to smooth out the PWM signal. So it removes the high-frequency component and reconstruct a continuous waveform that represents the original signal. So the cutoff frequency of the low-pass filter is very important. So it must be high enough to pass the original signal, but low enough to block the high-frequency components of the PWM signal. So the cutoff frequencies effect is if it is too high, the FC is too high, then the high frequency PWM components can pass through, but the output contains a ripple or noise. But if the FC is too low, the desired signal is attenuated and the output becomes distorted or weak. Moving on to its PWM demodulation circuit. So the PWM demodulation uses a 2-op amp, the LTC6244, and an RC low-pass filter, wherein R4 is equals to 10 kilo ohms and C2 is equals to 1 nanofarad. Excuse me. To recover the original analog signal from a PWM waveform The first op-amp, the U2, acts as a buffer or comparator stage that contains the incoming PWM signal, ensuring a clean transition between the high and low levels. The second op-amp, the U3, works with the RC network to smoothen the high-frequency switching of the PWM signal. So this idea is that the duty cycle of the PWM encodes the amplitude of the original signal, and averaging the signal over time reconstructs that amplitude. So the RC filter determines how well the PWM is smoothened, and its cutoff frequency is given by the equation of FC is equals to 1 over 2 pi RC, wherein a properly chosen cutoff frequency removes the switching frequency while preserving the original signal waveform. So if the cutoff is too high, ripple remains. So if it is too low, the output becomes sluggish and distorted. So the op-amp after the filter ensures that the output is buffered and stable. So producing a clean analog waveform that matches the original modulating signal. So moving on to its output. So the waveform plots the three signals, which are the original signal, the top one or the blue one, the PWM signal, which is in the middle one or the green one, and the demodulated output, which is the bottom and the red one. So the PWM signal corresponds, I mean, the PWM signal varies in pulse width according to the amplitude of the sine wave. So the wider the pulses correspond to the higher amplitude, and the narrow pulses correspond to the lower amplitude. So this confirms the proper PWM modulation behavior. So the bottom waveform demonstrate that a successful demodulation. So the red output closely follows the shape of the original signal, wherein a small ripples of or slight deviation may still be presented due to the incomplete filtering or RC limitation. So, but overall, the envelope is preserved. So this proves that the low-pass filtering process effectively arranges the PWM signal, reconstructing the analog input with good accuracy. So in conclusion, these experiments demonstrated that the PWM effectively converts analog signals into pulse signals. And with proper demodulation, using a low-pass filter, the original signal can be accurately recovered. So the cutoff frequency plays a crucial role in achieving a clear and undistorted output. So this is my proof of performance of doing the activity. So let's pass through this. So that is all. Thank you for listening.